Hi everybody, welcome to our next topic in physics today. What we're looking at today is a special class of motion called simple harmonic motion. This is something that pops up in physics a lot, and so we want to talk about a couple things around it, but first of all, let's define what this thing really is. And so simple harmonic motion is defined as the periodic motion in which the restoring force, and hence the acceleration, is proportional to the displacement for this object. So let's start breaking this down, and we'll start with periodic motion. So periodic just means repetitive or in a pattern. And so simple harmonic motion will be this repetitive pattern that keeps happening. And the force, or the acceleration, either one, because of course Newton's second law says the sum of the forces is equal to the acceleration. But switch this acceleration is proportional to its displacement. So what that means is if you double the distance away from your center point, you're going to double the force that's pulling it back. And it's going to be a restoring force, which means if I'm pulling it to the right, the force will be to the left and vice versa. So one of the really simple examples of simple harmonic motion is a mass on a spring. Um, and why that's so nice is because, well, we know that, well, hopefully after looking at the force required to stretch a spring, that if I double the force of a spring, you know that, or double the stretch of a spring, you know that doubles the force. And if I quadruple the stretch of a spring, it quadruples the force. So there's that nice proportional displacement idea here. And so if we see this thing bouncing up and down, we can see it is a periodic motion, it's repetitive, um, and it is going to have this restoring force that's proportional to its displacement. So a couple things we can kind of glean from this little example here. One is a pretty cool idea of if we graph position versus the velocity of this particle or this mass, we can see that it goes around in this complete sort of loop. And what that means is when the position is the lowest it could be, the velocity will be at zero, because again, when it's there, it's stopped, and at the top, it's also stopped. And maximum velocity is going to occur when the position is somewhere near the middle, which is again right here. And that matches up very nicely. And notice that again, it's never leaving that circle or that path, so it's always this periodic repetitive motion. Another way to look at it is if we graph this object's displacement over time, we get this nice sinusoidal curve. And so what we can see from, again, examining the system a little more is that the energy in this system switches between three kinds of energy. So we have kinetic, which is the energy of motion. We have elastic potential, which is how much stretch there is in the spring. And we have gravitational potential, which is how high or low this object is. And what's important here is that if I took all of these and added them up, the sum of these things would be a constant. That the energy stored in this system does not change. It just shifts from one object or one type to another, but it just flip-flops. And so we have this constant sum of these three forces. And what our goal is for today is to look for an expression for the period of this object. So how long does it take it to do one cycle? What factors does it depend on? And I'm going to warn you here that it does get a little hand wavy. I have to make some sort of assumptions here and go through it. And if you want to skip this next part, you can. I'll put the time of when this derivation ends in the link here so you know where to skip to. But if you want to skip ahead a little bit, you can skip a couple minutes ahead, and I'll draw you back when we get to the end. But in order to get the period, let's take a look at a simpler expression or a simpler system. Let's remove the gravity entirely. So we'll deal with something that's horizontal. And we're going to have this mass that we pull and let go. And so it's going to bounce back and forth, back and forth, back and forth. The sum of the forces on this thing will be equal to ma, as always. But the only force that we're concerned about here is the spring force. And that's going to be negative kx. And it's negative again because that's the direction that the force is applied on the block. If I do a little rearranging, I get that the acceleration is just equal to k over m times x. And this is important to notice, this does verify simple harmonic motion because the acceleration is some constant, k over m, times x. So we have this proportionality between acceleration and displacement. All right, so we've got this, and let's try and think of something and link this to something we know a little better. So we know a lot about circles. So we can actually imagine that we're looking at a circle here. Because if instead of a mass on a spring, we were just looking at something going around in a circle under uniform circular motion, and only looking at, let's say, the x direction of this motion. So imagine looking at a bicycle wheel edge on and watching a little point on there. You would see it flip back and forth from left to right, left to right, left to right. And it would actually follow, if we just graph the motion, this nice sinusoidal pattern. So we can steal a lot of our ideas that we have for circular motion um, to explain sorry, we can see a lot of it here, some circular motion to explain simple harmonic motion. And so let's start with what our expression was for the acceleration under uniform circular motion. And if we do that, what we can see is we can actually recycle some of these. So let's rearrange this so it's in terms of period, because again, that's our goal. And the first thing we're going to do is say, well, the period is given by uh, some constant times the square root of r over ac. But if we look up again at our analogy, the radius of rotation here is analogous to the amplitude of this thing's motion. So the further out you pull it is like increasing the radius of this wheel that's spinning. So I can replace the r with the a. But something else we can kind of say is that the amplitude and centripetal acceleration is kind of the same idea as the displacement over the x acceleration. So I can replace this with this and end up with this guy here. And then if you remember what we found it on the last slide, the acceleration is just given by negative k over m equal or times x. And so I come up with a simple expression for the period of the motion. So again, I told you if you're a little confused there from about 3 minutes to about now, don't freak out, because again, I'm just going through the process with you. But what I want you to get, what I need you to get is right here. So the period of a simple harmonic oscillator, which is just an object undergoing simple harmonic motion, is given by this expression. And the frequency is just the inverse, because frequency is 1 over period. So if I wanted to make something take longer to rotate, or to, move up and down, I need to increase the mass or decrease the spring constant. And of course, the opposite for the frequency. So again, if you were confused there in the middle, don't freak out. This is the big takeaway, these two things right here today, that we have the period expression and the frequency expression, and they're pretty simple. All right, so let's try these in some examples. All right, so our first example, we have a mass on a spring. We're going to pull it down by 0.55 meters and release it. And then, of course, we're going to see simple harmonic motion. And I've told you the frequency we observe is 2.5 hertz. What that means is every second, there will be 2.5 cycles. So this thing will go up and down 2.5 times in 1 second. All right, so I want to know the first thing, what's going to happen to the frequency if I make any sort of changes here? So the first change I'm going to make is instead of pulling the mass down to 0.55 meters, I'm going to pull it down to 0.85 meters. So I'm going to ask what change will happen to the frequency. And if you notice, that would be a good this actually would be the amplitude. But amplitude doesn't appear anywhere in our expression. So no matter how much I pull it down, it's not going to change how fast or how frequent this rotation or this vibration is. And so the amplitude does not affect the frequency. So for I, there will be no change. And we can say the same thing for 2 or II. Even though we're pushing it up as opposed to pulling it down, there still will be no change in this object's frequency of vibration, because it doesn't matter how much you pull it up or push it down, all that matters is the mass you're dealing with and the spring constant. But the next one we can look at, we can see it should probably make a difference here. We're going to change the mass. So the mass was 1 kilogram. Now we're going to use a 4 kilogram mass. We want to see what sort of frequency it will have, because it used to be 2.5 hertz before. So to do that, let's write out a couple things. So the first one is just the frequency expression right up here, but I'm going to give it some subscripts. I'm going to call it F1 and M1, because if I have M1, which is 1 kilogram, the frequency is going to be F1. So this would be 2.5 hertz and 1 kilogram. And I can do the same thing for F2 once I've made the changes. Just the second mass gives me the second frequency. And we also know that the mass of the second one is equal to 4 times the mass of the first one. So what I can do, and I will do it here, is I'm going to replace M2 with 4M1. So that's what I've done here. So I'm going to write it like this. And if we work it through and kind of get rid of this 4 and bring it to the front, I'm taking the square root of 4, so that's going to be 2, and it's on the bottom of a fraction. So I can write F2 just like this, that F2 is a half of 1 over 2 pi root k over m. And if we look, what is this equal to? Well, oh my goodness, it's just this guy here, which is F1. So we come up with a pretty simple expression here that in this case, F2 is a half of F1. So if F1 was 2.5 hertz, F2 will now be 1.25 hertz. Or significant digits, it should then be 1.3 hertz. So there's the frequency of my vibration, 1.3 hertz. Make sense? Awesome. So let's move on to the next part then. when we're dealing with this system, we've got a spring, we've got a mass, we know the mass, but what the heck is a spring constant? Hopefully you can see this one isn't too challenging. All we need to do is look at our expression and rearrange it for K because we have F, we have M, and we can use either F1 or F2. They're both going to give us the same answer. But I rearranged this for K, and K turns out to be 4 pi squared mF squared. Just rearranging this expression and shove some numbers in. I get 246.74 newtons per meter, and then rearrange that, or sorry, write that in significant digits. We have 2.5 by 10 to the 2 newtons per meter. All right, so if that makes sense, there's kind of our simple plug and chug sort of a question. And let's do one more here. So a spring mass system is set up to create simple harmonic motion. We need a frequency of 5 hertz. Describe a setup that could do so, that could create a frequency of 5 hertz. So what we know is we want this guy here to be 5 hertz. 2 pi is a constant. So we're left with K over M. We don't have K or M. But what's cool here is that we actually have, well, really an infinite number of solutions that would work for this. We're going to have pick any K and any M we want to get a frequency of 5 hertz. So one option, well, let's just pick a K. So let's pick a K constant of, let's say, 100 newtons per meter. And if I work this through and find out what my mass needs to be, I end up with this expression here and shove some numbers in. I'm getting a mass of 0.1013 kilograms, or I can write this just as 100 grams. So there's certainly one option that works. Another one would be, I don't know, anything else. I can actually make this to whatever the heck I want to make this work. Pick any K and find the M that works. And actually, that's not 100 grams, that's 101 grams, pardon me. Get out of there, 101 grams. All right, so there's again another sort of calculation question. One last thing I want to talk about before I let you go is this cool idea of damped harmonic motion. So we've always, so far today, assumed a friction-free environment. So that means that there is no friction. But what's going to happen if there is friction? And what I think you're going to see, or what you can imagine anyways, is that we'll end up with this sort of function here, that we have this same sinusoidal curve, but it's actually going to be decreasing in amplitude every time because we're draining energy away, or useful energy away from the system. So it's not all going to be in kinetic and potential anymore. We're going to be losing some to like sound or thermal energy. And so we actually have this decreasing amplitude. One thing that's really important though, is that if we look, the period of this motion would be exactly the same for all of these. So whether I'm looking at this cycle to this cycle, we'd have the same period as if I'm looking at from this cycle to this cycle. Every single period will be the same. And I can kind of hand wave argue for that because notice that our period does not involve the amplitude at all. So even though we're losing energy, we're not going to be changing the frequency or the period of this rotation, or pardon me, vibration. And a couple cool applications of this idea are things like car shocks, or bathroom scales. So if you imagine, well, I don't think you have to imagine, you've probably been in a car when you've gone over a bump, your car vibrates up and down a little bit, and it would actually be this motion here. You would want it to decrease amplitude pretty quickly because you don't want your car to bounce up and down forever. But you also don't want it to just be a hard stop and have this end too quickly, or else it'll be very jarring. And so car shocks are designed to slowly but continually reduce the amplitude of this vibration to make your car settle down. Another example you may have seen if you have an old bathroom scale that has an actual needle on it that moves around, that anytime you step on the scale, the needle will move above your weight, below your weight, and kind of bounce around and eventually settle on it. It's the same sort of idea here, because you're going to have this decreasing amplitude for this vibration. So what I want you to do, one of the questions on the little follow-up today is going to be, give me another application of this. Where else have you seen damped harmonic motion? So I want you to think about that, and then when you've got it, you can tell me what you've got, and we'll look at all your different applications in class next time. All right, guys, I hope this wasn't too bad for you. And again, if you were confused by this part in the middle where we kind of derived it, don't freak out. All I really need you to get in the end for those 2 slides is this is how we get our period and our frequency. So let me know if you have any questions, and I'll see everybody in class later. Have a good night, guys.